All right, thank you all for coming. My Keystone presentation is about investigating adversarial attacks as a solution for privacy from face recognition. And we'll talk a little bit more about what that means. So the face recognition model is a technique within machine learning, and specifically deep learning, which is used to identify a pair of two faces and determine whether the people in the faces are the same person or not the same person, essentially. The way it works is we train this machine learning model, and then we're able to perform in testing later, take those any two faces using the model that we've trained, extract the features, so like all the relevant things that you look for to tell if faces are similar or not, and then calculate the mathematical distance between those two feature sets to tell if they're the same person or not the same person. Now, the issue with this is that it can be very easily abused in various aspects of society. And one of the most prominent examples of the way it's been abused is this program called FindFace, which was designed for the Russian social media site VK, which is basically like the Russian Facebook. It was used by police to identify suspects, and unfortunately in Russia, sometimes that can also mean political dissidents. And it was also used by people on the internet, like 4chan, to anonymously find and dox sex workers. And that also, for people who don't know what dox means, that essentially means to anonymously leak their private information, such as their address or phone number. So we know that having an online presence is essential to maintaining professional and social relationships in today's world. We want our images to be identifiable to our human friends and acquaintances, but not to computer agents. Which brings us to how do we attack this system? So there is another technique in machine learning, which is sort of known as an adversarial attack, where we can kind of manipulate the input data, add some noise that we generate through our own system, and then use that to try and fool the classifier into assigning it a false label. So we have a classic example here that's often cited in papers, where we have an image of a panda, we apply some noise to it, and now the computer thinks that this image is of a gibbon. So going back to this facial recognition model, we find that we can attack the model by looking at these sort of testing pairs, and that when we apply some noise here to one of these pairs, we can then fool the system into no longer thinking the images are the same. So there are two main ways of going about this. There's the white box approach and the black box approach. So with white box attacks, we know the underlying model and we can attack it with this knowledge. So we sort of know more about the algorithm we're working with. And in the black box attack, we do not know the underlying model and we can only query it for classification. So we'll take two images, we query the model, we see if they're the same person, and then we can do that over and over again until we find a way to now fool the model. Now, as a consequence, the image can sometimes look much worse. The noise that was created by a gradient can make the image look unnaturally fuzzy or otherwise, not very good to human eyes. And these images might not be that noticeable at first glance, but if you take a closer look, you can probably spot some of this noise in the background that really adds this layer of fuzziness to the back of the image. So when we're testing sort of our data, for machine learning, a classic data set that people use, and I use in my project, is called Label Faces in the Wild, or LFW, which just has lots of public images of celebrities and various other figures. So for our training data set, we just took a random subset of 500 pairs of faces from this data set and used those to test our techniques on. Now, with the attack process, we're using a technique called the Natural Evolution Strategy, or NES. So as you can see, we start with two images of Angelina Jolie here. And if we look at the distance, we've seen that we have this distance value, right? And when we do testing, we find that the threshold for the classifier to identify an image as different should be about 1.14. So right now it's below this distance. So let's say these are both of Angelina Jolie, that's the same person. But then we perform some amount of queries and check each time to see if we're now increasing the distance or whether we're not. And if we're increasing the distance, we keep on adding some amount of very slight noise to the image in that direction, right? So as an example, we are now at query 2760, and we find the distance is over a threshold, which means the attack is complete, even though maybe the image doesn't look that different to us now. The computer now thinks these are different people. So one really important piece of these attacks is this parameter called Epsilon, and this kind of tells us about the strength of our attack. If we're using a very strong attack, that might complete very quickly and in very few queries, but might make the resulting image look very, very different or very fuzzy, then that would be a fairly high epsilon. So here we can see an example with epsilon 50. But we can also use some intermediate values like 30 or 16, and we can kind of see that these look much, much closer to the original. It might be harder to tell the difference. So our goal is to find this sweet spot epsilon value where the image doesn't look very different to us, but again, will still fool the computer. So in this project, we had some tested epsilon values. So as an example, here's our original image, and here's the match image that we use to test the distance. And here are the various epsilon values that we tested across for this project. So everywhere from 10 to 20. Now, in our experimental setup, we want to first test the attack strength. So we take our 500 pairs of images, we run the attack on all these images, and we see if the network's full within 10,000 queries, whether we can fool the network without having to ask it what the distance is 10,000 times. And then our attack strength is a percentage of attacks that do succeed, that do fool the computer within these 10,000 queries. Then we want to test the attack perceptibility of humans. So we get a random set of 100 images. Some of them will be these original unaltered images, and some of them will be attacked in altered images. And we give 10 tests out to 9 people each, where each test has 10 of these images, and we ask them to tell us whether they think they've been altered or not using an example. After giving them an example of what you saw before, they can very clearly see what an altered image might look like. So here's an example of the human testing setup. This is all done through Amazon Mechanical Turk, given out to random people for about 10 cents a piece. And we just ran these attacks across all these different epsilons to see how well people could recognize these images. And we found here that we had an attack success rate, which increased pretty steadily, as you would expect. The higher epsilons very clearly do produce higher attack success rates. When we look at the human attack detection rate, we also managed to find that there is this very strong correlation that as your epsilon increases, your human attack detection rate goes down, but perhaps not in as steady intervals as you would see the computer success rate go up. So this really indicates to us that we're able to sort of fool people and find a sweet spot, but we do really need to manage this epsilon because people can start telling quite fast. And we can see here again that same trend when you look at only the altered images and how they performed on those, as opposed to how they performed on those unaltered images as well as a control. This is only the altered images. We also see that it increases at a very similar rate, which shows us that there really is this correlation. So now, as to the impact of this research, prior research really didn't test in the same way how perceptible these attacks for the humans, and not with this same setup. We show that there really is this trade-off, but we can have effective attacks that are also imperceptible, and that future work should really look at the transferability of these attacks, which means that in addition to looking at how perceptible these attacks are, we want to see if that perceptibility we can also correlate with how effective these attacks are against not just one classifier, but a range of classifiers. Now, the reason this is important is because a lot of times in today's world, people will have you believe that there's this trade-off between privacy and sophistication in the world of technology. But this is really a false dichotomy, right? Advancements in new technology give us the ability to eliminate privacy and also to secure it. So creating this dichotomy is really how people might seek us to get rid of some of our privacy and accept a lower level of technological sophistication. But we really can have it both ways. We really can develop technology that not only helps give us these advancements in our sophistication, but also is really able to protect our privacy in addition to that. So thank you all for coming. Special thanks to my advisor, Professor Sarah Bargle, and PhD student Nathaniel Ruiz, who really helped me at every stage on this project. And I'm now ready to take questions.